So we can cover this one in a day. It's not that complex. So there is a level of complexity that gets with one really complex, one not so complex. So we start off with this, we get down to here. Okay, these are things you already know. I mean, you already know that. What's interesting is, I don't know if anybody really ever calculates this, but if you calculate this and put this number, the gravitational constant in, and the mass of the Earth, and then the radius of the Earth, not that it really matters, but they probably should have made you do this. And so if you think about it, take the mass of a little object out here, like the mass of one, and then put in there the gravitational constant, the mass of the Earth, and the radius of the Earth squared. Believe it or not, you'll get 9.81 out of that. Whoa, this is like a trick table. So I don't know if anybody ever made you do that, but or you can put in the other units and get 32.2, or you can move further away. And as you move further away from it, your gravitational constant drops off. So this is just like statics, except on the right-hand side, you don't have zero anymore. And so what you did in chapter 12 is you spent a lot of effort finding the acceleration. And the reason you did that is because you already supposedly knew how to do that. So now you have an acceleration component. And so there's some dude under acceleration. And then he talks about a system of particles. The system of particles, what does that mean? Well, if you had a block like this over a pulley and you released it, then obviously this is going to pull and go that way, and that's going to go that way. So what you'll have is M1. So here's an M1 and there's an M2. And they're somehow attached to each other. And so what you do is, and we'll see these problems in a while. We'll do an S1 and an S2, and you'll figure all that out. So that's nothing new. It's just I'm putting it into context. Instead of just looking at a bunch of marbles in a blob, there's actually a reason you do system of particles. Then he gets down here. Okay, that's G is the center of gravity there. Then he goes down, he says, okay, well, it has to be satisfied in each coordinate direction. So if, for example, this is kind of a weird thing, but let's say you had something floating in a box, floating in space, and you suddenly pushed it this way, you're going to change its direction a little bit. But, and what we'll find out in a little bit is that there are other things that happen too. And it's better described in polar coordinates instead of Cartesian. So, something can happen in the x coordinate, then nothing may happen in these two. In that case, it would be this. You're going along the x, and then suddenly somebody pushes you in the x. What happens in the y or the z? Nothing really. So they're separate. He does come up, I will say this, he goes down and he ties him, makes this comment here. We figured out the constant acceleration equations from the last chapter. So if you had this and you had some of the forces in the x direction didn't change and the mass didn't change. So in other words, if this is constant and that's constant, then the acceleration of x is going to be constant. So that's kind of where this is kind of focused on. That doesn't always have to be the case, but so here's a simple case. I mean, you take the thing, somebody's pulling this with a 400 Newton thing at 30 degrees, and he's going to want to know something about it. So the first thing you want to do is break the thing apart into a free body diagram. He's going to give you the coefficient of friction, which obviously was 0.3, but if you look back up here, there's his coefficient of friction stuck in there. The crate is this. He wants to know the velocity after 3 seconds. So what you're going to do is you're going to put a constant acceleration on it. I mean, a constant force. As a result, you're going to get a constant acceleration. And then you can work your way through that. So what do? Last time, or before, you had zeros here. Now, you have the mass of 50 times the acceleration in the x. This one, the acceleration of the y, it's not going this way or that way. It could, if you made this too high, it could jump off the surface, but that would be the case if, and this would work out that way if this were larger, if this force were larger than the weight. And this would come out here if you ended up with a negative NC, then somehow you pulled it too hard, leaped off the surface. So in other words, you can assume this, but if you've got a negative value here, you're going to have to go back and say the assumption that it's not accelerating off the surface is wrong. But then we have a positive value. You turn around and stick it back in here. You get a number here and a number here. Divide by 50 and you get your acceleration. Well, what do you do then? Well, you can do this. You can go back to the constant acceleration equation, or he might ask you, or in this particular case it'd be x. He might ask you how far it moved. And then you'd have something like this. That's a square right there. So he might ask you how far it moved in 3 seconds. So you use that equation, which is the constant acceleration. Then you look at this. This is pretty common to actually write the equation and do a free body diagram like this. So this is the m times acceleration component, and this part is the sum of the forces. Often people don't do this one because it's pretty obvious, and there's only 2 terms in there. When I say 2 terms, for 2 dimensions, you could have this, some 50 times acceleration in the y and 50 times acceleration in the x. But in this case, it's not moving in the y, so he never did anything like that. So, I mean, you could have all sorts of different things. But see, here's something that's a little bit different. 10 kilogram projectile is fired from the ground with an initial velocity. Determine the maximum height which it will travel. Atmospheric resistance is measured as this. So you'll get your 50 meters per second. You have your equation of motion here. He's calling, okay, I was about to say, he's calling that Z. And then he basically goes in there and says that this is the constant acceleration equations, ends up with that. This is kind of a weird and bizarre. Then you've got one like this. Okay, this is if you had air resistance, which he says the force of the air is resisting this is that. So if there's air resistance, it's certainly not going to go as high. It's not going to go 127 meters. How high is it going to go? Well, unfortunately, with this equation, you've got, okay, so dv dt, and you're going to have to move this thing over. And so what you're doing is you're moving this underneath here, and you're having to do a v dv because, in other words, this term is equal to, dv dt. You're going to have to move this up under, well, all of this up under here and take the dt and move over to the other side. So it has an integration, ends up with a little bit less than that. So he didn't go as high. And this is actually moderately accurate. In other words, people have run this in the wind tunnel and found out that drag force is proportional to velocity squared. So it's incumbent on somebody to figure out what that coefficient is. Run an experiment, do something like that. Okay, so then you'll find that these things get repetitive in a while. So here he's got a baggage cart, 900 pounds, 500 pounds, and 325. Oh, okay, here we go. And then he's, for a short time, driving frictional force developed by the wheels of the truck is that. The truck starts from rest, that makes it easy. Determine the speed after like 2 seconds. So there's a couple of things you could do. One is just do it as a big clumpy mass. Okay, so his 40 t squared becomes this. And then what he's got is 900, 550, 325 divided by that. That gives you the mass. I don't think that's the... So anyway, this is the mass of all those things together. And this is the pulling force right here. And so you just have that. Now that you have that, you got to work your way through this. You know, dv dt is equal to acceleration, but the acceleration is equal to that. And so you just got to stick that, take the dt over against this, and you'll have an integration. And then a really dumb one here. So they're pretty much easy to do. This one I won't even talk about because I want to save this one for the energy methods. But we'll glance at it. I wouldn't assign anything like that. But imagine if you had friction here. So see, he has no friction. Okay, so he has no friction. And then he says, okay, you're going to 2 kilogram collar, I guess that's the collar, attached to a spring with the stiffness of this, an unstretched length. If the collar is released, determine the acceleration of the normal force of the rod and the collar at y is equal to 1 meter. So it's 1 meter down. And so he basically just does a free body diagram, does the forces off of it and the acceleration. He basically puts over here, realizing that it's not going to go to the left or to the right. He comes up with this, and he ends up having to combine it together with the fact that this is at an angle. And he works the thing out. Now, what we'll do, I'll come back to this one when I get to the energy methods, because this one could be complicated to the degree that it's almost not doable in this section. But when it comes to energy methods, it's really easy to do. And so, all right, so this is where you got, this is the fun part, where you've got multiple masses, and they're attached together. Their motions are dependent upon each other. So notice what he does. When he does an extra part here, what he does is he does this part as the extra part. I don't know that I would do that, but hey, he says, if I take this and have a tension here and a tension here, well, this one's twice that tension. Given the fact that this has no mass and has no friction. Okay, so if it has no mass and no friction, that's the case. Then you can just take that 2t and put right here. And now what are you doing? You're basically looking at block A being that. And then you've got another block. And so you say, well, the t is common here between these, but is the motion common? So then you write the free body diagram. You write, here's your free body diagram. You write the equations If you look at this for a minute, you have two equations, but you don't know t, acceleration x, or acceleration of b. So you have two equations and three unknowns. The key is, how are these two masses motions are connected? Is acceleration A connected to acceleration B? And that's where you start doing this rope equation. You take two derivatives instead of one, and then you can have a relationship between acceleration of A and acceleration of B. So really, technically, what you got is one equation here, a second equation here, and a third equation here. And you've got unknowns of t, acceleration A, and acceleration of B. So you can actually solve that pretty easily. And so he just does that and solves it right there. And so I'll come back and do some of these, but I think I'm going to jump into the next section. You can see these are kind of, I mean, here's the same problem that was up there. It's really hard to generate a lot of different problems. And these are the ones that are easiest to generate. You can generate a lot of problems with lots of pulleys, and you might be able to generate something like that. But the rest of them, I mean, here's a guy pushing a block. I mean, how simple is that? And you got this, okay? That's not that hard. That one is a situation where you do, here, hang on. You have the weight of A, the tension here, and the weight of B. So there's nothing, the weight of B doesn't go back like that. So it doesn't really have anything. It says neglect the weight, coefficient of friction, and the mass in each block is determining acceleration. No, so I think this is supposed to be symbolic. So on A, well, first of all, if this is the equation that's the positive, and this is the positive, it's pretty simple that acceleration of A is equal to acceleration of B. And then what you do is you write the equations this way. Sum of the forces equal to, what do I got? If this is positive, I got weight A minus tension equals to the mass of A times acceleration. I'm just going to call that acceleration. So you'll get an equation that says that weight A minus tension equal mass A acceleration. Over here, believe it or not, you're just going to get sum of the forces. There's only one, and that's the tension equals mass of B times acceleration. Well, you could just add those two. You get weight A equals both of these masses, MA plus MB over acceleration, and then you take this and divide it under here. So they're basically moving as a group, but the only thing that's pulling them is the weight of A. The weight of B doesn't do anything. So it's just simply things like that. They're fairly simple problems. That's a fun one because it's got lots of pulleys, but and this one too. I like those. The rest of them are somewhat repetitive. So what does he want to get into next? Well, there's only one other really thing. Well, there's this, and that actually, I don't know why, but in my mind, I always attach this to polar coordinates as well, because they are essentially the same thing. So here's a situation where you've got a tangential and a normal acceleration. And so all you're doing there, look, the problem set's already over. So all you're doing with here is you're dealing with that. V squared over R, or rho. And that's pretty much it. Okay, so here you got a mass that's attached to a string. If you look at it, here's your mass. This is down where your string is right here. And so he wants to write this as the normal, and this is the tangential. And so what he's saying here, he's saying there's some friction there, okay? The maximum tension in the cord can sustain this die, And the coefficient of the kinetic friction between the disk and the platform is that. So it starts spinning. And so all you're doing is sum of the forces in the normal. That would be this direction. And the only thing you got is that T. And then you've got V squared over rho, or 1. And then you got the T, the tangential motion. And so what he's got is this, which actually, this is what this is. So his normal to the disk, to this disk equation tells you that this is equal to that 29. So I don't know what the mass of the thing was. Oh, sorry, 3 kilograms. And so then you just got 3 equations. And you actually end up with, oh, and he asked another question too. Maximum tension, but there was something else, something related to the speed, because anyway, how long it took for that to, but these are, they're all the same in a way. The most complicated thing you do is to find this, and in these cases, basically that's constant. And guess what? I mean, the problems don't last that long. They're not that many. And here's the part that really gets you. And the reason being is because it's hard enough to find these terms, but there's an extra complication here that he throws at you that really is not necessary. And let me explain it, try to explain it to you. So you got tangential and normal, and you got a particle coming through here following this blue path. Then he comes in and he does this. Okay, so the problem is you throw this in there, and it's just annoying because what he's actually doing is he's wanting to split and find, like, say, this component or this component in the tangential direction. Okay, so here's your path. So let's look at what he's actually doing here and why you don't really need to do all this. So the blue, which actually, here, let's make it blue. The blue is actually the path of the particle. The tangent is some defined term that is tangent to that path. Well, what is tangent to that path? The velocity is tangent to that path. So if I wanted to know that direction, and this was a unit normal that is tangent to the path, I would find the velocity and I would divide it by its magnitude. Instead, he comes up with some weird mess here that he has this term here and all sorts of stuff. And it becomes like, you look at it and you feel like you're going to vomit. But at the same time, if you come back and really look at what this is, it's nothing more than the tangent to that path is nothing more than the velocity, the direction of the velocity. So that's a complication that's unnecessary in my mind. And I have a problem that I worked. I'll go find that one because that kind of describes it. So here's the complexity, and I think I assigned something like this in the homework. Here's the biggest part that you're dealing with. So you have some object that's spinning about here, and as it spins, this collar sits up here. So he really wants to know the forces here. Well, let's see if I can do a decent job. Here is the unit vector in the theta direction. And here's the unit vector in the r direction, which actually he kind of put here and he kind of put here. However, because the ring right now, or the tangent to the path of the particle being this thing, is this way, here's your tangent, then it's pretty easy for this normal to be described, but it needs to be broken into, hang on, its components along each direction. And as it turns out, this force is pretty straightforward because it's, the arm is pushing this way. So what you end up with, let me try to get all this complexity off here now. You end up with this being the component that is right here. This component is that, going in the negative R direction, because he decided that was going to be the positive. And then you get this one, hang on. This one is the component going that way. So if you look at it, this is this vector, and it's going the opposite direction. You see that. And then you just see this F force here. So the tangent didn't play too big of a role in this one. So you end up with that. And guess what? The only thing you don't know is, well, you'll have to find your R dot, your R, and your theta dot, which I'm guessing, okay, constant angular velocity of that. So that means theta double dot equals 0. So he went in and did this. Oops. And then he evaluated it at 45. He went and did the R dot, evaluated it. R double dot, evaluated it. And then what did he do? He came in and he did this to find the value that's supposed to go right there. And then he did this to find the value that's supposed to go right there. And so this is directly out of chapter 12. And so these are this is a rarity for that to be the case. I would not expect that don't expect that to be the occurring again. So look at this. And so you get that. That's all you have. Okay, so you can get stuff like this. Here is the same thing. Now here's a case where the object, okay, and this one's pretty obvious because if I was swinging it this way, this ball might not be confined to that surface. It could lift. But if you had a channel that was like this, you would have to make an assumption that this ground is pushing this way, but if it was in a channel like this, you could assume it that way. Which one would you assume? Just assume one of them and let it give you a negative answer. So this is one that he could have added that complexity to show that. So in fact, you've got the ground pushing on this drum or whatever that is. You've got, okay, let me see if I can do a decent job here. You've got this rod right here pushing on the drum. So if you pulled that drum out, you'd have this. Okay, hang on. You'd have this. And I don't know how to do this, but it should have some sort of weight. I don't know. And so he's got that. Oh, okay. He puts his weight right here. He puts the FP, which is the rod here pushing on the drum or whatever, and he's got the ground pushing back up on this. So he's got his free body diagram. Turns out the FP happens to be going here, but it turns out this one and this one are going to have to be broken into components. So this one broken into components, and this one broken into components, and the FP is just going in the theta direction. And it looks like this drum is 2 kilograms or whatever. So you look at this for a minute, and basically he has to realize that he has to come up, you have to come up with r dot, r double dot, theta dot, and theta double dot in order to get the acceleration in the tangent and acceleration in the normal. So this is what he does here. He goes through, okay, hang on. He goes through and says, oh, this is the equation. That's awful, because now you got to take its derivative, then you get this for its derivative, and then you take the derivative of that, and I don't know whether to box this one or that one, but you know, you get that, and now you have to evaluate it at whatever angle that is, which happens to be 60 degrees. So then you put in this 60 degrees into these two formulas, you'll get the 3 R's. Now, what he said before, it was what was it was a half of radians per second. Okay, did he say it was a constant rate? So therefore, if it's constant, that's 0. And so if you look at the r double dot, you see a 0. You see a r, you see that. Here's your, I'm sorry, that was theta dot, was this. Theta dot squared is that. And then you got this r from right up here. And so you're just taking all those values and finding the actual value for here and here that you're going to have to take and put both of those back in the acceleration equation. So the key is, he's working these problems in this sequence where he does the equations of motion and then he does the kinematics. I would probably do the reverse. I would probably do the kinematics first because that was from chapter 12. And then I would do this. But it doesn't really matter. They're both completely independent. So after you substitute those back in there, then you will have a number here, a number here. You will not know this and you will not know that. And that's what you're solving for. Okay, this is the one that's, okay. So here's a situation where you have to use that tangent. And I think maybe this is the one I did in that video, but I'll go find that, because what you find out, his first thing he does is he goes in and does this. And if you're comfortable with doing that, that's fine. But to me, if I go in and find the velocity, and by the way, you know, the velocity is nothing more than, okay, r dot ur plus r theta dot u theta. So there's the velocity. And since you already have to find r dot and theta dot and r, you can actually find this vector pretty easily if you do the kinematics first. You do the kinematics and you can basically get that. Now, the funny thing, I don't know if we have time, but if we do, we could try this. Let's try this for a minute. I think I have enough room. If I take his numbers, take his r dot. So here, I'll just write this down. What is the velocity vector? Well, it's r dot 0.4 ur plus r theta dot. R theta dot. Where's theta dot? Well, his theta dot was 4. So his 4, that's the theta dot. But what is the r at that point? Wait, what is his theta at that point? From what I can tell, the theta, wait a minute. You see what his theta is? I mean, it looks straight out to be 0, but that can't be because this is what he's showing. Okay. That does not make sense. This is r Okay, this is really okay. So can C is a mass that moves along the groove horizontally. The slot forms a spiral. Okay, so he's saying it's doing like that. So he's showing this other part, but he's saying it's this. Okay, so then he says, which is defined by the equation of that. If the arm rotates at a constant rate in the horizontal plane, and if the force exertion, so theta is equal to pi. Okay, so 4 pi u theta. Now the question is, if I have a vector that goes like this, and it goes out 0.4, and it goes down 4 times pi, what's the angle? So he's shooting for this angle, looks like. Wait a minute. Why does he have this one? And then he's got that one. Oh, okay. So here's his. I'm going to find that one. So what is the inverse tangent? Okay, so if I'm doing this on that, I think it's arctangent of, is it the 0.4 over the 4 times pi. Oop. It won't like that. We'll see what it does. I don't know what it's going to do. Have y'all ever done this with trig? Let's see if it even recognizes it. Ooh, I got that wrong. Well, okay, it can't work it out. It doesn't like trig for some reason. So in any case, he ends up okay. Do I have those in reverse? No, I don't have those in reverse. Anyway, it's getting too close to the end. Well, anyway, you can do this off of the tangent or his equation, either one. And then there's only one thing left in the whole section, and that is, and actually, I don't think, yeah, we'll skip that part because it's got the asterisk on it. So that's it. I don't think there's anything more there. Yeah. And what we'll find in the next section, so the hardest ones are the ones with the tangent, with the, the hardest ones in the subset are the ones with the tangent on. And those are not as easy to find unless you've got some odd pattern like this that they're going on. The rest of them, like something like this, is straightforward. But so that's chapter 14 in a nutshell. That's so we got, if we left now, I would be cheating you of about 5 minutes. Does this make sense? I mean, really, there are two types. Okay, so there are 3 types of problems. That the way I look at it. The one type is just a simple block, like on a plane being pushed or at an angle, and that's really straightforward. The other is pulleys. There might be a pulley system in which there might be some sort of weight being pulled. I'm just making something up. Okay. So here you might have something like that, different weights. These are 3 individual equations, and their accelerations are tied through these ropes. And then the third type I think of is related to this type problem, these type problems, and that's it. There are the ones with the normal and tangential, but I kind of look at those as being a subset of the polar coordinate. And usually they're easier because like this kid on the swing, it's just a constant radius of motion, and he's swinging back and forth like a pendulum. Constant radius out here. Now you can't have ski jumpers and stuff like that, but I don't know that I see any of those. Constant radius, constant radius. Those are all constant radius. Not seeing. Okay. Oh, here's the only other one that's oddball, and that you find your radius of curvature by taking here you take the y prime and the y double prime, put them in that equation, and that'll tell you that r, or in our case rho. And so that's pretty much it. Oh, well, I guess you got, okay, well, this is the cylindrical. So if y'all are fine with that, then we could come back after spring break. You'll find energy equations are incredibly, make something that's unsolvable using these methods and makes it very solvable and almost jokingly easy. So y'all did, well, I don't know, but you are in mechanics and materials or something like that, or you will be. The energy equations are somewhat related to, either directly or indirectly, depending on the way you view it, the virtual work that you did. Did y'all do that in mechanics and materials, where you had kind of put a dummy load on it, take the derivative with respect to that dummy load, all that sort of stuff? So it's kind of related to that, although we really don't take a derivative when it comes to energy methods, because what you find is that energy in is the energy out, and it's conservative, makes it so you can find your answer pretty easy. However, if you got into an advanced dynamics class, virtual work helps you a lot. Then you get into Lagrange equations and things like that. So, but anyway, I'm going to call it quits.